Hey folks, Mrs. White here. Today we're going to look at linear programming. That's going to lead us into our discussion on optimization. And linear programming is really similar to stuff that you've already done in the past. You're going to be looking at a system of inequalities. So those are our graphs that are dotted solid shading. And since it's a system, it's going to be overlapping shaded areas. And more specifically, we're going to be looking at overlapping shaded areas and then their vertices or the corners of each. Because what's really cool about linear programming and optimization is that all of the best combinations of things happen at those vertices. So today we're going to focus on not writing linear inequality systems from word problems because that's pretty tricky. We're going to get really good at the mathy part of linear programming. And then when we get together in person, we're going to spend some time really unpacking some word problems and applying the math that we're going to practice and learn about today to those word problems. So it might seem a little weird to maximize and minimize something that doesn't necessarily apply to anything in the real world, but know that we're going to be moving towards that. But I thought it'd be better to have a discussion about word problems versus just do some notes from a flipped lesson. So we're going to get started. Hopefully you've grabbed a note-taking guide. It looks a lot like this, but it has two examples on it, okay? So we're going to, let's see. We're going to start off with our first example here, okay? Optimization with linear programming. It has the 3 is less than or equal to y, which is less than or equal to 6. So right now, looking at this system, you may assume that it's going to have 3 lines, but if you look a little bit closer, right here is a compound inequality. It's actually 2 inequalities squished together into one. It's an and statement. So our first step is going to be to break that into the 2 separate inequalities. One of them is going to be our first piece. 3 is less than or equal to y. And the second one is going to be including our middle piece again, the other symbol and the 6. So y is less than or equal to 6. Now you can see that each of these are going to be their own lines, and they're either going to be vertical or horizontal. So let's start by graphing it, okay? That is our directions here to graph the following systems of inequalities. So if we're given only one variable and a constant, and we're told to graph it, we're going to go to this axis, okay? And we're going to put a dot at this value. So here's our y. In fact, we'll full screen this. Here's our y-axis right here. We're going to go up to 3 and put a dot. Now, our line is actually going to be the opposite of the axis it's hitting. And because it's an equal to symbol right here, I can tell that it's going to be a solid line. So I'm just going to continue this line in both the positive and negative directions. Now, unlike an equation, in addition to dotted or solid, I also have to determine shading. So here, my y is greater than 3. So if I think of my y-axis, the shaded region is all the values that are going to be greater than 3. So if this is 3, everything above it. So I'm going to shade everything above this line. And I'm done with this yellow piece. Now I'm going to go to the green line. I'm going to go to the same axis. I'm going to go to the y-axis, put a dot at 6. So 1, 2, 3, 4, 5, 6. It's horizontal again, and the line should be solid. Okay. Now this time our y must be smaller than 6, okay? Which means that if this is 6, all of the y's in the shaded area are smaller. Now, because we're dealing with a system of inequalities, we really only care about where these green shaded and orange shaded is going to overlap. So as my shading for the green comes down here, okay, I really don't need to shade in below this orange line since it's only going to be single shaded, and I'm looking at every single time these shaded regions are overlapping each other, okay? So I'm really only looking at or isolating this one rectangular shape right here. I'm going to continue. I got 4 inequalities I should be graphing here. Again, these both are going to be solid because they have the equal to. I'm going to start here with y is less than or equal to 3x plus 12. So 1, 2, 3, 4, 5, lost at 6, 7, 8, 9, 10. I'm just going to assume 11 and 12 above. Normally, I would go up 3 forwards 1 from here, but I can't. There's no reason to either. I want to see where it hits these 2 lines here. So from 12, I'm going to go down 1, 2, 3, backwards 1, down 3, backwards 1. Ooh, I hit that green line perfectly. Down 3, backwards 1, another perfect intersection, down 3, backwards 1. Again, equal to means solid lines. I'm going to connect those lines on that graph. Now, even though it doesn't line up perfectly, I can see one of my vertices is going to be here and here, okay? So I'm going to keep that in mind because my next piece that I'm going to have to do is outline what the vertices are, but I should finish up my shape. The shading here, again, if kind of using logic like we did on these two doesn't really work for you, you probably want to plug in 0, 0. So I'll be left with 0 for y is less than or equal to. When I do 3 times 0, it cancels out. 0 plus 12 is just going to be 12. So I can ask myself, is 0 less than or equal to 12? If the answer is yes, I go to where 0 is. That means this side of the blue line, okay, this entire side here would be shaded. Now, I don't need everything here. I only need to shade the items that are already double shaded and make them triple. So I could shade down here, but it's not really pertinent, and I could shade above here, but it's not really important either. I only shade where it's going to result in a triple shaded area. Now I'm at my last line, and hopefully you're feeling like this is very familiar because we have done it a bit. Looking here, solid line, it starts at 6. Oh my gosh, perfect intersection again. And this one's going to go down 2, 1, 2, forwards 1. Down 1, 2, forwards 1. So there is an intersection here, but I can tell it's not perfectly on my grid lines. Okay. And then I'm going to connect those dots. Again, I don't need to make a huge graph here. I'm just looking at where it crosses the other inequalities. I can test the point 0, 0 if that's what you like to do. I plug a 0 in here. 0 plus 6 is 6. The 0 is smaller than 6, so 0, 0 works. That means I'm going to shade in here. So my feasible region here is a closed shape. It's this trapezoid. Okay, it has those two parallel sides. And my vertices are found where each of those lines intersect. So one of them is very obvious. This one here was -2, 6. So I'm going to write that over here. -2, 6. On your sheet, it should be written below the graph, I think. This one isn't bad either. I'm going to go -3, +3. I'm going to come over to this one here, my coordinate pair. I didn't go over left or right, so it's 0 and up 6. And then this coordinate pair is not intersecting very nicely. Okay, now you might not realize it, but I do know half of my coordinate pair here. All right, and we'll talk about that in a second. If you're not sure exactly what to do at this point, we have other strategies for solving for vertices when they're not nice. It's substitution or elimination, whichever one's going to be easiest. So I'm going to take my equation for this orange line, okay, and rewrite it over here. And instead of writing it as an inequality, I'm going to write it as an equation because I want to figure out where this orange line equals this red line. Okay, where they're equivalent to each other is where they intersect. And then I see that orange line is intersecting my red one. I'm fortunate I get to color code, and my red one was this. So again, I'm going to write it as an equation. Y equals -2x plus 6. So looking at these, if we're trying to find the intersection point between these two, you have two options, substitution or elimination. I really hope that you notice you should do substitution right here. We already have our y alone. In fact, we know that the y value of our coordinate pair is going to be 3 because it says y equals 3. So I'm going to take that 3 and plug it in. And then, oops, I'm not going to plug it in for x. Be very careful, right? We want to plug it in for the y value, okay, not the x. We're trying to figure out what x equals. So slow down. Make sure you don't make the same mistake I almost just did. So it's going to be 3 equals -2x plus 6. So I'm just going to solve, subtract 6 from both sides. Divide by -2, divide by -2. I get 3/2 is my x value. Now, hopefully you recognize that's 3 divided by 2, which is the same thing as 1.5. And we can double check that this coordinate pair is reasonable, okay? If we look over at our graph, if we go over 1.5 boxes, right, 1.5 for our x, and up 1, 2, 3 for our y, that's pretty darn close to where our point is. Remember, our graphs aren't perfect. If we had gotten something like 7, 3, we definitely didn't go over to 7 and up to 3, okay? So this seems like a reasonable answer. I now have all 4 vertices. None of these items should feel that new to you. What's new with linear programming is taking each of these really important points, all 4 of them, and plugging them into either a profit or a loss equation. And this is on the back side of your sheet. We're going to start working. I'm going to scroll the sheet down, but you can flip yours right over. To go forward with maximizing or minimizing, we're going to have our profit-loss equation right here. And every one of our coordinate pairs where the vertices happen is a point of interest. So we're going to re-record all of these coordinate pairs into our table. So we had -2, 6. We had the coordinate pair -3, 3. We have the coordinate pair 0, 6. And then the last one we just did substitution for was 1.5, 3. Now, what this is saying is that if we take each one of our coordinate pairs, remember f of anything is just function notation. So this function's name is f. We're going to plug a point into it and get out an answer. So I'm going to essentially have f of -2, 6 equals, and I'm going to replace in this equation the x with -2, right? Because that's where the x was, -2. And I'm going to replace the y with 6 and solve. So instead of 4x, I'm going to put 4 times -2. Instead of -2y, I'm going to put -2 times 6. And I should rewrite this work down here. So I'm doing 4 times -2 minus 2 times 6. Well, 4 times -2 is -8, and -2 times 6 is -12, and -8 and -12 together is -20. So that's the answer when I plug that coordinate pair in, is I get out a -20. And I'm going to follow that same process with all of my coordinate pairs. And what happens is eventually I'm going to get numbers that are different here. The one that's the highest results in the maximum or the highest profit or loss, and the minimum is going to be the lowest possibility if we took into consideration this formula. So we'll just plug those in quickly, make sure we have it nice and clear in our notes. We're doing 4 times our x value, the x is -3, minus 2 times our y value, which is 3. So 4 times -3 is -12, -2 times 3 is -6, -12 and -6, -18. Now I'm going to plug in 0 for x. Minus 2, and instead of y, I'm going to put in my 6. So 4 times 0 is 0, and then 2 times 6 is 12, so -12. And then lastly, I'm going to plug in 1.5. Now, I know this might trick some of you up. You're welcome to use a calculator, okay? But I would encourage you instead to kind of think through it. I'm going to do 4 times 1, which is 4, and then 4 times a half, which is 2. So 1.5 of 4 is going to be 1, which is 4, and then the half, which is 2, so 6. So this is just 6 minus 2 times 3, which is 6. 6 minus 6 is 0. So in this instance, the maximum that you're ever going to get, if you take into consideration this profit-loss equation, the highest money you could make, you could say, would be 0. The minimum amount of money you could make, well, we go to our smallest number here, which is going to be -20, meaning you would owe 20. Okay? Again, this feels weird because we're not dealing with a word problem, but we're going to work on writing all of the systems and writing this profit and loss next time that we're together. So now let's take a look at a second example, okay? In the first one, when we started out by graphing our system, okay? And we're going to do the same here, but this time we really only do have 3 equations to graph. We don't have a compound inequality in any of these. So we're going to start by graphing. Then we're going to find our vertices, and then we're going to take those vertices and we're going to maximize or minimize them by plugging them into our profit or loss equation. So let's start off with this first line. I am not ready to graph it yet. I need to get this y alone and positive. So I'm going to start by moving 3x over here by subtracting 3x from both sides. Then, to get this y alone, I need to divide by 2 to each piece. Now, I'm dividing by a positive 2. I don't have to worry about changing the orientation of this sign. If I multiplied or divided by a negative, then I would have to. Now it's obvious what my graph's going to be. I'm going to start at -6. I'm going to go down 3, forwards 2. So -6 is going to be 1, 2, 3, 4, 5, 6. I'm going to go down 3, forwards 2. I'm also going to go up 3, backwards 2. And in my first line, I really do want to fill up my grid. Okay. I'm going to do a solid line. And I could test 0, 0, or I could kind of say my my shaded area is going to be bigger than my line. Here's my line. Bigger than this line, bigger than the y-intercept is going to be here. If you plug in 0, 0 to test the origin, you would get true. Now I'm going to go to my next line right here. It's already y alone and positive. I'm going to start it at 12. But you're like, hey, Mrs. White, the highest my graph goes is 3. Should I come up 9 way off this grid? The answer is no. Okay? Instead, when you're in a situation where they're giving you a specific area, and this is very intentional. I gave you only this part of the graph because this is where the shape is that's of interest. Okay? It's not up near 12. You can start this line essentially anywhere on that line, meaning you can find any point on this line, graph it, and then do your slope from that point. So assuming this is 12, right, on 0, it'd be going up 12. My slope is up 3, forwards 1. That means at 1, it's going to be 15. At 2, it's going to be 3 more, which would be 18. Wow, that's going to be high. I want to come back this way because my slope's going to be coming down, right? So maybe I'll start and pick -2 and imagine but calculate what my y value is. So again, I'm thinking I want to come backwards here. Let's see what happens at -2. So I'm just going to kind of do some work here. I'm going to make an xy chart. If my x is -2, I would have -2 times 3, -6, go towards the positives 12, my y would be 6. So -2, 6, I still can't graph. So now I'm going to find another point, maybe -3. Well, -3 times 3 is -9, go towards the positives 12. That gives me a +3 for my y. So -3, +3, yes, I can graph that. So now that I'm here, I don't have to continue my table. I can just do this slope. Instead of up 3, forwards 1, I'm going to go down 3, backwards, backwards 1, down 3, backwards 1, down 3, backwards 1. And again, in this one, I do want to fill in my graph because I'm not exactly sure where the other line is going to intersect this, okay? And whether down here is going to be an important area or not. I do see this vertice is going to be nice coordinate pair, it hit perfectly. So I need to do shading. I could use logic again. Y must be smaller than my line. So here's the axis. My y-intercept would be here. That means I'd be shading below my y-intercept. I'm only going to shade in, even though I would technically be shading in this region over here. I don't care about it because I only care about where it overlaps. And it happens to overlap pretty much everywhere the red does on this graph. Okay? Excluding this little triangle here would be single shaded red, but we don't care about it. Okay? Now on to our last line in this system. We'll do this one as green. I'm going to start at -6 again. Oh my gosh, it hits perfectly. I'm going to go up 3, forwards 1, up 3, forwards 1, up 3, forwards 1, and make it solid. Now you might say, Mrs. White, I thought you said that in this graph we'd see all the important points we need. We don't see where the green and the blue are going to hit each other. Okay, are they going to hit each other down here? Are they going to hit each other up there? Hopefully you're saying to yourself right now, oh, they're parallel. Look at those slopes. They're parallel lines. They're the same slopes. They're increasing at the same speed. Okay, their rate of change is identical. So they're never going to intersect each other. What that means is that our feasible region, our area that's going to be shaded 3 times, is going to be an open shape, okay? And it's open because it's not going to have a side up here. It's going to be bounded here, and here, and here, and it's not bounded here, so what we're going to call this feasible region is going to be unbounded, okay? Because it's not a closed shape. It doesn't have, it didn't create a perfect triangle or a rectangle or a trapezoid like our first one. I'm getting a little ahead of myself. I should look at where it's going to be shaded. Is it going to be over here? And then this would be our unbounded region. Is it going to be over here? And then this becomes our unbounded region. Well, using logic again, our shaded area should be greater than our line. So our shaded area, here's our line. We're thinking of the y values that are greater than it, meaning I'm going to be dealing with this. So I'm going to shade here. And it does become what you think would be like a rectangle, but essentially this is continuing up, triple shaded forever, folks, all the way off. So our vertices, there's only 2 of them, one here and one here. If we have a system of 3 lines, you can have up to 3 vertices, but that doesn't mean you're going to necessarily have 3. You could have 2. You could have that this line, the green one, started here and maybe only 1 vertice. So I'm going to now write the coordinate pairs for each of those vertices. There's only 2. One of them is over 0, Down 1, 2, 3, 4, 5, 6, negative 6. This one is 1, 2, 3, 4, negative 4, and I didn't go up at all, negative 4, 0. So we've done our graph, we found our feasible region, which in this example is unbounded. I found my vertices for where those lines, or the corners, excuse me, of the unbounded or bounded region happen, and I recorded them. Now we're going to flip our sheet over and we're going to use these two coordinate pairs to maximize or minimize using a special equation, okay? And again, they gave us that equation. We're not writing it right now. We weren't given a word problem. So 0 and negative 6, I'm going to record it here. And negative 4 and up 0 was our other coordinate pair. I use this formula. So the name of the function is f. I'm going to plug in a coordinate pair for x and y and get out an answer. So I'm going to have 9 times my x, which is 0, minus 6 times my y, which is negative 6. Well, 9 times 0 is 0. Negative 6 times negative 6 is positive 36. Next, I'm going to plug these in, this for x and this for y. So 9 times my x value, which is negative 4, minus 6 times my y value, which is 0. Well, again, that cancels. So I'm really just left with 9 times negative 4, which is negative 36. Well, the minimum and maximum, we only have two numbers, okay? One of those is the minimum, negative 36, and one of them is the maximum, which is 36. Now, if these two were the same, then you wouldn't have a maximum or minimum. If you had several points and the two highest were the same, you can't have two maximums if that's what you end up finding when you plug things in. So this is the start of our conversation on optimization. When we get together next week, we're going to practice this mathy piece one more time, and then we're going to start applying it to word problems, which can be a little bit trickier. If you look at the bottom of the worksheet I gave you, it does take a look at a word problem. Just read it over and be prepared that this is going to be the start of our discussion when we get together next week. Thank you, folks, for taking the time to watch this video. I hope that it kind of set you up for success next time we get together. Make sure you have that note-taking guide filled out and completed so I can check it off when I see you next. Thanks again, and bye.